Get your clickers ready. Get your clickers ready. And let's begin lecture. It's such a beautiful day outside. Let me pop this down a little. Okay. I like to, you know what I used to do in one of my previous places of employment? We used to have class on a nice day like this. We would have class outside. Yeah, but you guys, first of all, this is too big of a group, and second of all, we're too close to the ice cream kiosk. I know you guys you'd be blazing over there in about 2 seconds. Yeah, harmonic oscillator is nice, Dr. B. Let me get an ice cream cone. I know what you guys do. All right, so we're going to do a hanging oscillator problem, and it's going to require some brain work. And Brian Green, I already coordinated with him, our learning assistant. He's, Brian, where are you at? I just saw you. Okay, he's up there. Raise your hand and hold it up. Right, there he is up there near the top row. He's going to come circulate around, and you can pepper him with questions and stuff. And I may give you a little bit of time to work on this hanging oscillator problem, but we'll work through some of the basics of it first. And then I'll show you some interesting things about damped oscillation, which is basically an oscillating system with some kind of a friction or drag force involved. And then I'll talk about homework. And by the way, your homework is going to be a study assignment. The written homework coming up, our do-over special, I'm going to give it out on Friday. It's going to be due on Wednesday. And that means that office hours next Tuesday, 1 to 2 p.m., just come on down, and if you still need help with the homework, just slide over there. If you can make it. If you can't make it, you can't make it. We had a bunch of guys in there yesterday working on stuff, so it's good. So we'll do that next week. All right, let's keep going here. Now, from chapter 16.3, this is a little bit blooped up here, the different layers. Suppose you attach the object with mass, or an object with mass, to a vertical spring, originally at rest, and let it bounce up and down. You release the object from rest at the spring's original rest length. And that's a subtle point. Go ahead and jot that. This is actually a problem in 16.3. And then it says, show that the spring exerts an upward force of 2 mg, 2 times the weight force, on the object at its lowest point. So that's maximum extension. So we're going to be working in delta y's. It's hanging vertical. Did you guys do a hanging oscillator in lab? You saw one? Okay. Yeah, spring with a mass on the end of it. And it just, yeah. And we're going to be talking about that in just a second in the context of this problem. B. If the spring has a force constant of 10.0 newtons per meter and a mass of 0.25 kilograms, if it's set in motion as described, find the amplitude of the oscillations. Okay, so we're going to do that. And then C, find the maximum velocity. We're going to do that. All right, so here's your hanging oscillator. Go ahead and sketch it in, and it's just hanging. At this point, it's attached to the ceiling, and it will extend a little bit to support its own weight. Okay. So if you put it on horizontally on a tabletop like this, its relaxed length might be 11.5 centimeters, about like this. But hanging it might be, like 12.1 centimeters or something. Okay, a little bit longer. But anyways, so you have this relaxed state, and this is before adding the mass. Now this problem, I've figured out the solution to it. The wording is a little bit tricky, so let's just work through this step by step, and we'll just go 50-50. um, right through this problem. All right, so we're going to call that y equals 0. The position of the spring in its relaxed state without a mass. Now we're going to attach a mass, and then it becomes an oscillator. But this point here is going to be important for another reason. All right? So we want to, and we'll just keep our vertical bookkeeping set up so that y is equal to 0 at this point where it's, you know, in its relaxed state. Now, next step, you attach a mass at y equals 0. All right, so there it is. And it's mass m. And the thing about it is, at this point, if you attach a mass, it ain't going to stay at y equals 0 unless you exert a little bit of upward force on it, you know, with your fingertip. 0.25 kilograms, that's about half a pound. So you could go like this with your fingertip and hold it up good. All right. So now I want you to add a free body diagram for this configuration. All right. So make a dot. And your applied force, the red arrow is upward. That's U. And then the weight force, you know, the weight force of that mass, you know, 0.25 kilograms times 9.8 negative, and that's your weight force. That's downward. All right. So now at this point, you attach, and the way the wording is, you release it from rest. So this has to be an equilibrium up here. Right? You're holding it in place. In other words, V is equal to 0 up here. All right. Now make sure you write that down. V is equal to 0. All right. Support. All right. Now, you have to hold it up there with a few newtons. And the reason for that is the spring isn't doing jack. The spring is relaxed. I mean, you've attached it there, and as soon as it dips below y equals 0, yeah, then the spring's pulling upward. But right now, it's not pulling upward. It's attached, and you're pushing upward, you know. And so what this means is, as soon as you release it, there's going to be a position y1 below there, and I'll just type it in. Here it is, at which the spring force minus ky, that's going to be upward, because all these y's are negative. I mean, 0 is up at the top, and y1 is, you know, whatever it is. We don't have it specified yet, but that's going to be a negative number. Okay, so minus ky minus k 10 times negative something is a positive number. So your force is going to be upward here, and at some point at just the right y1, it's going to be equal to mg. Now we know that the mass of this thing is 0.25 kilograms. So we can figure out the weight force. We can figure out y1. It's not that bodacious. All right. So that's where we start. And then, and let me pause for questions. These free body diagrams are important. Go ahead. Negative ky is the spring force. It's always F equals minus kx, or F equals minus ky, or F equals minus kz. You know, whatever. You know, F equals minus k theta if you're doing an angular oscillator. You know, this example that they use in the textbook of, you know, you flick, you hold a ruler, straight edge, plastic one, and then you flick it a little bit at the very top, and it'll oscillate. It'll go back and forth a little bit, and that's an angular oscillator. So anyway, so minus ky is the place, you know, and at y1 you don't have any spring force there, or excuse me, at y1 you don't have this force anymore. You've got this one. So you attach the mass, you have a new equilibrium, and you let it bounce up and down, and the lower turning point is at y2. So now here v is equal to 0 again, and now you're going to start turning and going back upwards. All right. So if you think about this, You can, if you think in terms of, you know, y equals 0 is maximum compression or maximum height. Y2 is minimum height, maximum extension. And Y1 is the new equilibrium, all right? And for that reason, you can write this down. Kinetic energy 0 at the top. It's also 0 at the bottom. Because there's going to be a point down there where the spring is going to be able to start accelerating this thing upward, all right? It's going to drain off all the downward momentum and start giving it some upward momentum. That's the way springs do it. You know, it'll overshoot equilibrium if there's no drag or friction or anything. It'll just keep going up and down. And if you're in the lab, you know, you have a hanging oscillator and a good quality spring, and it's not too extended past its you know, a useful limit. If you don't extend it too far, it'll keep going, you know, for a good long while, you know, until somebody bumps into it or whatnot. So you let it bounce up and down to the turning point, and here's Y2, the turning point, kinetic energy 0. What else was true down there in terms of energies? What else is true? Come on, think. No, nothing's constant. Not on an oscillator. Everything's changed except for the total energy. Yeah. Potential energy is max down there at Y2. So, yeah. So that's, yeah, it's also maxed out up there. The two extrema of your oscillator, whether it's this kind or any other kind, the two extrema, max potential energy. All right. And that's because the potential energy function is 1/2 kx squared. That's basically a parabola. So it looks like an upright parabola, and it's symmetric with respect to displacement x, or in this case, displacement y away from equilibrium. Right? So both of those babies, they're the same distance apart, and therefore they're both max potential. Question? If there's friction, it'll eventually stop at Y1. But if there's no friction, I mean, if you're in a vacuum, you know, like down at up at Langley Research Center, NASA Langley, they have these wind tunnels where they evacuate them of air, or not a wind tunnel, but they have these chambers where they test spacecraft, and they basically evacuate the air. So you can do the famous experiment of, you know, dropping a feather and a hammer at the same time, and they fall at the same rate, just like Galileo did at you know, at the Leaning Tower of Pisa. But, you know, so yeah, Y1 is where it would, you know, if there's no drag and in air, there's not much drag, you know, until they start going really fast. So this thing would keep going up and down, but you'd see, you know, you'd be able to map it out, you know, the high point, the low point, and then halfway between that is theoretically is equilibrium. So that's Y1, right? Yeah, it's always moving unless there's some drag on it. Okay, and eventually it'll settle down to 0, you know, but it might take a little bit of time. And if you're in that special chamber with the air evacuated out up at Langley, at NASA Langley Research Center, you know, it's just going to keep going, you know. First name? Martin. Point Y? You mean Y2? Y equals 0, the top one? Yeah, it does. So what you really have to be aware of here is there's gravitational potential energy in action here. But if you now here's a point that is I can't go into with you guys because you don't have calculus, but you can prove that all that gravity does is extend the oscillation down a certain distance to a new equilibrium, and then all oscillations are the same. So if we pulled out, we're going to figure out the amplitude here, okay? If we had this thing on a horizontal table and pulled it out by the same distance, we'd see the same oscillation this way, okay? And so all that gravity does is it just translates everything downward by a few centimeters or meters, depending on how heavy your mass is. So the old equilibrium was up at y equals 0. The new equilibrium is down at y1. But all the physics are now, once you orient to the new equilibrium, just worry about the oscillation. Okay. All right. Question here, Rachel. Yeah, we're not really, well, we're going to figure out what y1 is. Okay. And what we know is that it's going to be moving at maximum kinetic energy there, minimum potential. But yeah, it's question here. If you have a really massive, twice as massive, twice the mass, 0.50 kilograms, it'll stretch out a little bit further, twice as far, until the spring breaks, within reason. Question? It'll oscillate in the presence of no drag or air resistance or friction. It'll oscillate between y equals 0 and y2. And the central point of there, the midway point between those two, by definition, is your equilibrium, because it's a spring. It's an oscillating system. It would settle down at y1 over time. Yeah. And so your amplitude. So after a while, you'd say, "Whoa, it's not going down to y2, and it's not getting all the way up to y equals 0." And it would narrow down. The amplitudes would narrow down until eventually it's right there at y1. All right, let's keep going. Okay, so you let it bounce. And just to make a note, these two distances are the same. So if you figure out one, we know the other. All right. Now, this is the force. F equals minus K1 when this is at Y1. All right. That's the equilibrium condition. The spring is now stretched. It's no longer at, it's not stretched to y equals 0. It's stretched all the way down to y1. So it's exerting some upward force, okay, as I have it diagrammed out. And of course, the weight force is all the way down. Now, this equilibrium condition will allow us to figure out the extent of, all these two vertical line segments over here. Right? So now, at y2, down here, we have extra extension, all right? So we have a bigger force, all right? And we still have the downward force of gravity, but now there's a net force. And there's always a net force at the extremum of an oscillator. Because if you're out to the right, you have maximum leftward force pulling you back to the left and dropping some leftward or negative momentum into the oscillator. If you're at max compression all the way to the left, the restoring force is back to the right, and you're getting maximum newtons to the right at the two extremums. Now, if you're just budged a little bit away from the equilibrium point, you just get a few newtons. But if you're all the way out there at max, you pull it out to the maximum extension, or you push it into maximum compression. That's where you have the maximum newtons, because you're at the furthest extension, furthest compression. All right, so that's what we've got here. And it's double the size. So whatever y2 is, it's double, the force there is double whatever the force was at y equals at y equals y1. So for that reason, it's equal to 2 mg. Now we've proven that the force at y2 is upward 2 times whatever the weight force is. All right. So so if k is equal to 10.0, now we can plug stuff in. All right, we're going to do that in a second. 10.0 newtons per meter. And this is a problem from your textbook, basically. Chapter 16.3, I think. And if the mass is 0.25, you can calculate it out to 0.49 meters for Y2. So Y is 0.49. So the amplitude of the oscillation is 0.245. That's half of that. So Y1 is negative 0.245. Y2 is 0.249. So you can figure out Y2 and therefore figure out Y1. All right, now here's your calculation. Minus KY2, Y2 is a negative, so minus KY2 is a positive upward, and that's equal to minus 2 mg. Now G is negative 9.8, so this is going to be a positive number here. All right, and so you just plug your stuff in now. You want to find out what Y2 is, just, put in 2 and times the mass, and then negative 9.8 meters per second squared, and then divide by K, and you'll get Y2 by itself. All right? And so that's how you tell your amplitudes. So the amplitude of oscillation is 0.245 meters, and you go from negative 0.245 meters up to 0, and then back down to 0.49, and then back up to 0, and then back down to negative 0.49, and so on. So there's your oscillation. Now we have the dimensions. I'm going to ask you a question on your iClicker. Now what we're going to do with the iClicker, it's going to be a numeric question. All right? And what you're going to do is I want you to work with your neighbors, and Kevin is going to circulate around and give you tips, and I want you to cooperate with your neighbor to calculate the maximum speed. All right, so here's your formal question. All right, now I'm going to give you a good amount of time with this. So talk to your neighbors, talk to Kevin, talk to your own brain. And hey, you guys, I didn't tell you how to do this. This is not practice. This is a problem. This is you guys figuring it out. But you should be able to figure it out. And calculate the maximum speed at Y1. And here's a, hi.
The professor, before you forgot to put
Yeah,
the mic
no.
on.
Yeah, you can put it up there. Good. I noticed that.
Yeah.
I knew he'd be back, or you.
Yeah.
Good. Thank you. You ready for a hint? I have one hint. A hint? Hints. So type in your speed, something point something something, and hit the send key. The ones that we just used. K is equal to 10.0 newtons per meter, and the mass The mass is 0.25 kilograms. 0.25, quarter of a kilogram. Yeah. Oh, didn't you take notes? You didn't take notes? Yeah, I did. You didn't write it down? Yeah, so Y2 is a negative something if you wrote it down in your notes. And then the top of the oscillation is 0. And guess what? I don't see any correct answers yet. So that's a little bit of a hint. And I see one person with a negative answer. Speed, if I give you, ask for a speed, just give me a positive number. Kevin, Kevin, man, lots of people to ask you questions. Good. It's as cold as ice. You must pay the price. I can't. Yeah, K is equal to 10.0 newtons per meter, and the mass is 0.25. Come on around over here, Mike. Some kind of what? Let me see your work. Put it down right here. That's all right. You might only see one variable. Let me see what you got. Oh, okay. So you want to talk about it? Well, think in terms of the energies. That's the hint. The energy diagram. Have we ever done an energy levels problem where we had to figure out a speed? Free fall. We did energy levels, basketball. Yeah. Now that was free fall, different completely system. But still, you can organize it in terms of potential energy, kinetic energy, and total energy. Right? So think in terms of those. And, so just try writing down an energy equation here. But now for the potential energy, it's 1/2 ky squared because it's an oscillator potential energy. All right? You're welcome. Is this your clicker? Okay. Here you go, man. Yep, no problem. Keep your hand up. Okay, I can see 134 answers. Let me give you 2 more minutes. Yeah, Kevin, maybe you could blaze across to these jokers up here. Danny, raise your hand. Danny, raise your hand. Raise your hand. Yeah, maybe those guys could use some mental counseling.
Distance between Y1 and Y2.
What's the distance between Y1 and Y2? Y, what's the distance between Y2 and Y1? 0.245 meters. One more minute. Yay, I see some correct answers. Nice. Uh, I want two decimal points, 2 decimal places. The second one is the one that you do round, and possibly the first. Yeah. Okay, 1 minute. Get it an answer. Give me your best, even if you feel like you're. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, Matt, you got it? Stop. All right, let's work it out. Here we go. We're going to think in terms of energy, so we're not going to do F equals ma or anything like that. I mean, you could if you wanted to, but it's a menace to society. But if you think in terms of energy, you're going to be copacetic. All right, so maximum elastic potential energy is equal to 1/2 times the extension from equilibrium y1 to y2. So that's y2 minus y1, and it's quantity squared, right? So, and you can calculate that out. And then that's equal to the maximum kinetic energy. Because remember, whatever is maximum at the extreme, that's the potential energy, disappears at the equilibrium, and then it's all kinetic. So you just go straight equality. So this is where you have maximum elastic potential energy down here. That's why I have this hint. And then maximum kinetic energy is up here at equilibrium, as always, for any oscillating system. All right, let's put in some numbers. Let's plug it in. All right, so the K is 10.0 newtons per meter. 0.49 negative minus a negative 0.245 quantity squared is equal to 1/2 mv squared. So m is over on the other side, 0.25 kilograms. And you can cancel the 1/2. I mean, it's not that bodacious, but you can cancel it if you want. And solve for v squared. So it's basically 10.00 times negative 0.245 quantity squared, which it doesn't matter that you have the negative in there because it's squared, but you may as well be accurate. And then 0.25 kilograms in the denominator. So that works out to 6.0025 joules in the numerator. Yeah, so that's also your total mechanical energy, E. It's also your maximum. Actually, that's half the, or that's twice the total mechanical energy. Anyways, you divide by 0.25, you get 2.401. So that's V squared. Now raise your hand and take a bow if you want. Stand up and take a bow if you answered this, because there's only 7 of you. All right. Good. Oh, there's a little cluster of geniuses over here. The genie eyes. All right, now, shh. Now, that is, students, that is what we call in the business a brain burner. And expect to see something like that on the final. Something difficult like that where you have to put 2 and 2 together. So you're going to see something, a brain burner, or as some people say, nifty. Like this little guy. He's in his little oscillating system there. Now, damped oscillation. Now, we're just going to look at some pictures. So this is a storybook. This is bedtime. We're doing a little bit of storybook action here. If you have friction in your oscillating system, it's going to rattle up and down, but the amplitude, and I've already talked about this in terms of the hanging oscillator. I mean, if there's a little bit of air friction, air resistance, it'll eventually get to that equilibrium point. And that's what this one's doing. You can see this. This is a a graph over time of the amplitude or the position x of something swinging left to the right with friction. So eventually, somewhere off to the right, it'll go down to zero. Now, this is for what we call an underdamped system. Okay, it's not overdamped. It's not. If it was overdamped, we would say it would take an infinite time to get back to equilibrium. All right, this one gets to equilibrium, but then it overshoots. So it loses a little bit of energy along the way, but not enough to stop oscillating. Now, here's the two exceptions. The red graph A is what we call a critically damped oscillator. The damping level is just perfect to try to oscillate back, but lose just the right amount of energy as it damps down to come right down to zero. B, the darker curve, is overdamped. It will do the same thing. Eventually, you'll get to zero, but it takes a lot longer. The critically damped case is the minimum get to equilibrium and stay there time. All right? So those are some nice diagrams from 16.7. Now, I'm going to do some elaboration on them. And let me just bring this point up. When we have an undamped oscillator, in phase space, it looks like this, a regular old ellipse. We talked about that at the wazoo last time. It has units of angular momentum for the area, and that's related to Planck's constant in a significant way. If there's damped oscillation, X max is going to get smaller and smaller. So every time you go around the ellipse, you're actually going to be dipping inward a little bit. And so what it looks like is something like this. All right. Well, it might not be a golden spiral, but it's going to spiral inward. And this one's actually a little bit tilted because of the initial conditions. But it goes smaller and smaller, just as this one back here. Oh boy, let me see if I can. This one here is getting smaller and smaller. Now, if you had one of these, you would start out at, like extreme X, maximum X, and then dip down to the origin. This one here, you're going to take several laps around the origin before you get down to there. Okay, so now the thing about this is, and I'll just give this to you. It's an insight from quantum mechanics. The Heisenberg uncertainty principle, if you've ever heard of that, raise your hand if you've heard of that. Good old so this is not Breaking Bad. This is, physics. Heisenberg uncertainty principle means you'll never get to zero. You will collapse all the way. And this is critically important in nuclear physics and also in astrophysics, because a star, when it goes into supernova, the core will collapse into a ball of iron. And if it's heavy enough, it'll continue to collapse. But eventually, the Heisenberg uncertainty principle will prevent it from getting smaller. And it'll stop. And that's when you get something called a neutron star. You've turned all the iron, all the protons and neutrons in the iron nuclei and the electrons into a big pile of neutrons. But sometimes even the Heisenberg uncertainty principle is not strong enough, and it'll keep collapsing, and that's when you get a black hole. So you're dismissed. Keep studying chapter 16. I'll see you on Friday. And we'll have a written homework assignment for Friday to hand out.